So hello everyone, as you all know this is Arpit Raj, the student of MSc Mathematics 4th semester, and today is my presentation whose topic is set functions, length, measure and probability related to MAM 402 measure theory. I heartily present this beautiful presentation to my respected sir Dr. Sunil Kumar Singh. Thank you very much sir for giving me a chance to represent myself in the class. So let's begin. So here is an object of this presentation. The object of this presentation is to be familiar with the set functions, particularly with the length function, and to the extension and generalization of length function called measure. After that we shall see few basic concepts of probability, and then we shall see a beautiful relation between measure theory and probability theory. This will definitely increase our interest as we are going to correlate pure and applied mathematics through this interesting presentation. So let's start. The first topic of this presentation is an interval and its length. So let us discuss what is an interval, its basic definition. So an interval is a subset of real numbers R which contains all real numbers lying between any two numbers of the set. For example, the set x belonging to R such that x is greater equals to 0 is less but is less equals to 1 is denoted as the square bracket 0 comma 1 is an interval. And similarly the interval a comma b such that x belongs to R such that x is greater equals to a but less equals to b is called a closed interval. And the interval small bracket a comma b is equals to x belongs to R such that x is strictly greater than a and strictly less than b is called an open interval. And the interval a comma b is such that x belongs to R, x is greater equals to a and but strictly less than b, and a comma b is equals to x belongs to R such that x is strictly greater than a but less or equals to b are called the closed open and open closed intervals respectively. These intervals are also called the semi-open or semi-closed intervals. And here the points a and b are called the endpoints of the related interval. Let's discuss what is the length of an interval. The difference of endpoints of each interval I, whether it is open, closed, semi-open or semi-closed, is called the length of that interval. It is denoted as Li. Thus Li is equals to b minus a, where a is less equals to b. Okay. So for example, you can take any of interval, say open interval 0 comma 1. So what will be its length is the difference of its endpoints, that is 1 minus 0. Remember that the length will always be positive number, so that's why we have to subtract the lowest endpoint from the greatest one. Okay, so in this way length is Li is given as 1 of the particular interval 0 comma 1. So let's move on. So here are some basic concepts. Since we know that length I is equals to b minus a, where a is less or equals to b, and now what if a equals to b? Means both the endpoints are coincide. So what will be the result? Let's see. Then Li equals to a minus a, which will give us Li equals to 0. In this case the interval has one and only one point, that is I is equals to singleton a, means the length of every singleton set a is 0. Now the next is the length of an infinite interval is infinity. Obviously, suppose we are taking minus infinity to open interval minus infinity to a, then what will be its length is a minus infinity, and that will give us a plus infinity, and which will be obviously infinity. So the length of an infinite interval is infinity, obviously. Third point is that the length of an interval is always greater equals to 0 for all interval I subset of R. If x is any fixed real number, then length of I is equals to length of I plus x. This property is called translation invariance. Actually, what is the translation invariance is, suppose we have an interval I and choose any arbitrarily number, positive or negative, 0, whatever be, any finite number, choose any finite number x and add it to each member of that particular interval I, and by doing this we can get one another new interval whose and when we are going to find out its length, then we will see that it has the same length as the previous one. So this property is true for all the intervals in R. So this property is called the translation invariance, and thus we have length of I interval I is equals to length of interval I plus x. Now the next topic is the extended real number system, R star. So what is the extended real number system? As we have seen above, that the length of an interval is always a positive real number, and also that the length of an infinite interval is infinity. Therefore, for the further study and analysis of such notions, the real number system R equals to open interval minus infinity to infinity is extended by including the points minus infinity and plus infinity, treating as actual numbers. This new number system is called the extended real number system, denoted by R star. Thus we have R star equals to R union minus infinity to infinity, and which will give us R star is equals to close interval minus infinity to plus infinity. And here the set 0 closed interval 0 comma plus infinity is called the set of non-negative extended real numbers. So so far we are familiar with the notion of real numbers. Okay, so how we need, what is the importance of the extended real number system? Actually, as we have seen so far, as we have seen above, that the length is always a positive number, and the length of an interval can be infinite also. For example, the length of an infinite interval is infinity. So for the further study and analysis, if we want to produce a function, if we want to introduce a function from the sets of all intervals of whatever the length of be, it may be finite or infinite, to the real number system, then in case of finite intervals, in case of intervals having finite endpoints, we can easily associate it to a number with the help of its length. Okay, but in case of infinite interval, we always have an infinite length, length infinity. So if we are going to introduce a function from the set of all intervals of R to the set of real numbers, then we always need a point infinity in R such that the length of an infinite interval is always infinity. But we know that the real number system R is an open interval minus infinity to infinity. So and we know that a function, if we are going to define a function from the open interval, the set of all intervals, so obviously its domain will may contain an infinite interval whose length is infinity. So for a function, all of its domain point is associated with the codomain via that particular function. So for the further studies and analysis of length, if we are going to introduce any function on the set of all intervals, whether it is finite or infinite, then we must have to include the point infinity plus infinity as an actual number to the codomain side. So it means we for the further analysis we will have to extend the real number system, which which is minus in open interval minus infinity to infinity, by including the points minus infinity and infinity. In this way we get a new number system which is called the extended real number system and denoted by r star, and such that r star is equals to my open interval minus infinity to infinity union minus infinity comma infinity, the 2 point sets. And in this way since we the real number system, actual real number system doesn't contain the points minus infinity to infinity, but here we are taking the extended real number system by including the points minus infinity and infinity, that is the end points also. So in this way we get a new number system which is called the extended real number system. So the function which we are going to define on it is called the length function. So let's move ahead. So here is the length of open and closed set. So far we became familiar with the notion of length of intervals, and now we are going to extend the concept of length to the open and closed sets. So here length of an open set. Let A be any open set in R, then we know that any open set in R can be expressed as the countable union of mutually disjoint open sets uniquely. That is A equals to countable union of intervals I, which implies length of A is equals to length of countable union of I, and which implies length of A is equals to countable summation of length of I. We found that the length of an open set can be obtained by summing the length of individual open intervals by doing whose union the open set A is obtained. So next point is, if A and B are two open sets in R such that A is subset of B, then length of A is less or equals to length of B, which is obvious. And for any open set A contained in A comma B, we have length of A is always greater equals to 0 but is less or equals to B minus A. Now we are familiar with the length of open set. Now we are going to discuss the length of a closed set. Let F be a closed set contained in some open interval A comma B, then the length of the closed set F is given by length of F is equals to B minus A, length of F dash, where F dash is the complement of F in A comma B, closed interval A comma B, that is F dash is equals to closed interval A comma B minus F. So here clearly length of F is always greater equals to 0. Actually how it comes, let us discuss. We are familiar that how can we find the length of an open set, and now we have to find the length of a closed set. So we know that a set F is said to be closed if it's a complement, that is F dash is open. So actually if F is closed, it means that F dash is open. As we have seen above, the how can we find the length of an open set, and we have, since F and F dash are the disjoint to each other, so obviously the length of F in A comma B will be length of A comma B minus length of F dash. So obviously length of A comma B is B minus A, and length of F dash is to be determined, we can find from the above discussion. So clearly length of F is greater equals to 0. So let's go forward. Now set functions and its properties. So let us see what is a set function and some of its basic properties. So set function, let X be a non-empty set and C be a collection of subsets of X, then a function F from C to 0 comma plus infinity, the extended non-negative real number, is called a set function. For example, length function is a set function. Means set function is any function which is defined from a collection of some subsets of a set say capital X to the non-negative extended real number. Okay, it is called the set functions. For example, we have seen in the previous sections that length is defined from the set of all intervals in R to the non-negative extended real number. In this way we can say that the length function is a set function. So now the properties of set function. The set function have the following properties. The first one is finitely additive. A set function f from C to extended non-negative real number is said to be finitely additive if f of countable union of ai is equals to countable summation of f of ai. Whenever all ai belongs to C are such that countable union of ai belongs to C and ai intersection aj is equals to 5 for i is not equals to j. The next is countably additive. A set function f from C to 0 comma plus infinity is said to be countably additive if f of countable union of ai is equals to countable sum of f of ai whenever all ai belongs to C are such that countable union of ai belongs to C and ai intersection aj equals to 5 for i is not equals to j. Similarly, countably subadditive. A set function f from C to 0 comma plus infinity is said to be countably subadditive if f of a is less or equals to some countable summation of f of ai whenever a belongs to C and a is a subset of countable union of ai and ai belongs to C for all I. So let's go forward. Now we are going to deal with some examples of set functions. So here first of all we are taking the length function and we will discuss that how a length function is a set function. Since we know that the length of an interval is a non-negative extended real number, thus if C is the collection of all intervals that is the subset of R, we can define the length as a function L from C to 0 comma plus infinity which associates every interval I to a non-negative extended real number called the length of that interval denoted as L of I. Since L from C to 0 comma plus infinity is defined by Li is equals to length of I for all I belongs to C, is clearly a set function. Okay, so in this way we have seen that how a length function is a set function. Now notable points: length of I is always greater or equals to 0 for all I subset of R, and second one is the length function is countably additive. The length function satisfies the property of translation invariance, that is, if x is any fixed real number then Li plus x is equals to Li. So let's go ahead. So here is the second example of set function, which is called measure, and our whole measure theory is based on this particular notion, which is called measure. So let's see what is a measure. Introduction is here. As we have discussed above how the concept of length is extended to the open and closed set in R, now we would like to extend the concept of length function to all subsets of R. Therefore, we think about a function m from C to 0 comma plus infinity where C is a collection, that is the sigma algebra. We all know what is a sigma algebra actually, of any subset of R satisfying the following properties. First one is MA is defined for all sets A belongs to C, and second one is m of I is equals to length of I for every interval I belongs to C, and third is m is countably additive, and fourth is m is of A plus x is equals to MA. This property is called translation invariance, as we all know. Such a function is called a measure. So here is the basic definition of measure. Let x be a non-empty set and C be a collection, that is the sigma algebra of subsets of X, then a set function m from C to 0 comma plus infinity is called a measure on C if first m of phi is equals to 0 where phi belongs to C, and second one is m is countably additive on C, that is m of countable union of AI is equals to countable sum of m of AI where AI is AI belongs to C for all I greater equals to 1 with countable union of AI belongs to C and AI intersection AJ is equals to 5 for all I is not equals to Z. Thus, a measure is a set function such that MA is defined for every A belongs to C and MA is greater equals to 0 for all A belongs to C, and M phi is equals to 0, phi belongs to C, and next is M is countably additive. So if anyone want to know that what is a sigma algebra, then I would like to introduce sigma algebra. Suppose we have X any non-empty set and C be a collection of some subsets of X, then C is said to be the sigma algebra on subsets of X. If A belongs to C, then its complement, that is A dash, belongs to C, and the countable union of subsets of X which are in C is also in C. So now we will see another example which is taken from the applied mathematics basically, which is also an example of set functions, which is the probability function. So before discussing what is a probability function, we should know some basic concepts of probability. So let's begin. So here the first notion is random experiment. An experiment which does not produce the same outcome when repeated under identical condition is called a random experiment. For example, tossing of coins, throwing of dice, etc., as we all know. So now probability: if there are n elementary events associated with a random experiment and m of them are favorable to an event A, then the probability of occurrence of event A is denoted by P of A, and defined as P of A is equals to the ratio of the number of events favorable to the event A and the total number of events, that is PA equals to m by n. So from the above it is clear that m is greater equals to 0 but is lesser equals to n, which implies that m by n is greater equals to 0 but is lesser equals to 1, which implies that PA, probability of A, is greater equals to 0 but is lesser equals to 1. Now the next is sample space, which is denoted as capital S. The set of all possible outcomes for a given random experiment is called the sample space associated with that experiment. It is denoted as capital S. The sample space behaves like a universal set for all questions concerned with the experiment. Now the event, which is denoted as capital E. Any subset of the sample space as associated with a random experiment is called an event, denoted by E or A, B, C, etc. Impossible event: the event phi, which is also a subset of S, is called the impossible event, and whose probability is obviously 0 because the number of cases favorable to phi is 0, as phi have no element. So the probability of impossible event is 0. Certain are sure event: the event S, which is obviously a subset of S, is called the certain or sure event. Clearly PS is equals to 1 just because the number of cases favorable to S is n and the total number of cases is also n. In this way, probability of S, the sample space, whole sample space, will be 1. Now we are discussing some special types of events. The mutually exclusive events: the two events A and B are said to be mutually exclusive if A intersection B is equals to phi, that is, each event is disjoint from the other. Complementary events: if A is any subset, that is the event of S. As we all know, any subset of S is an event. So if A is any subset, that is the event of S, then its complement E dash is also a subset, and in this way it is also an event of S. The event here, the event E dash, is called the complementary event of the event E. Since E union E dash is equals to S implies that probability of E union E dash is equals to PS. This implies that P of E plus P of E dash is equals to PS, and this implies that P probability of E plus probability of E dash is equals to 1. As we all know, probability of sample space PS, that is PS, is 1. Now the probability function: from the above discussion we found that first P of A is defined for all A subset of S and PA lies between 0 and 1, and second one is P of phi is equals to 0 and PS is equals to 1. Therefore we can define probability as a set function from a collection of events in S called sigma algebra of events 2, 0, 1 or 0, infinity. As we all know, 0, 1 is a subset of 0, plus infinity. So we can take our codomain 0, plus infinity instead of 0, 1. And so here is the definition, final definition of a probability function. Let G be a sigma algebra of events in the sample spaces. Then the function p from G to 0, 1 is said to be a probability function if it satisfies the following properties. First, for each e belongs to G, p is defined is real and p is always greater than or equal to 0, and ps equals to 1, and p is countably additive, that is p of countable union of ai is equals to countable sum of p of ai whenever ai is any sequence of disjoint events in S. So here the probability measure and probability space. Observation: from all the above discussion we concluded that probability of A is greater equals to 0 for all A belongs to G, and since range of P is equals to 0, 1, we can take a codomain P is equals to 0, plus infinity. Now since G is a sigma algebra and P of phi equals to 0 and P is countably additive, thus P is a measure on G. As we have discussed above, we can obviously observe that, we can obviously find that P is a measure on G, and this measure is called the probability measure. And next, the triplet S, G, P is called the probability space. In most elementary applications, S is finite and sigma algebra G is taken to be the collection of all subsets of S. So next, application of measure in geometric probability. In case of continuous sample space, the total number of outcomes of random experiment is infinite, hence we cannot define probability in terms of the number of points. Thus the classical definition of probability is modified and extended to what is called the geometrical probability, or probability in continuum. The geometrical probability P is defined as the ratio of measure of specified part of region to the measure of whole region. Here measure refers to the length, area or volume of the region if we are dealing with 1, 2 or 3 dimensional space respectively. Thus if measure in 1 dimensional space denotes the length, then it denotes the area, volume in 2 dimensional and 3 dimensional space respectively. So that's all about my presentation. So here are some references. So here is an acknowledgement, which is, I would like to express my respectful special thanks of gratitude to my respected Professor Dr. Sunil Kumar Singh for giving me an opportunity in the form of this presentation to represent myself in the class, which definitely increased my knowledge and confidence and gave me a unique experience. I would also like to thank you, sir, for your best teaching skills, hard work, simple, kind and supportive nature and perfect guidance, which always motivated me and raised my interest in the paper MEM 402 measure theory more and more. That's all about my presentation on MEM 402 measure theory. If anyone have any question or doubt, please ask. Thank you very much.